So myself is Dr. Pratyush Kumar, and I have completed my PhD from IIT Bombay itself, and from with my colleagues, we have started one company that is the iteraSim, and we are currently focusing majorly on the training session and workshop session into different institute, as well as online session on the CFD and finite element analysis. And this is our first session, which is a free workshop on the ABAQUS using means this webinar is going to be the first session. Then maybe if it suits you, then we may conduct some 1 or 2 months workshop, which will be going to be hands-on workshop on the finite element analysis. So before starting the session, let me introduce about the Arun, who is going to conduct this session. So this session is going to introduce about the fundamentals of the finite element method and its practical implementation using the ABAQUS. You will going to gain insight into the problem setup, meshing, materials modeling, as well as the boundary condition. So this is the live demonstration, and you will after finishing the session, you will able to learn the simulation workflow in the structural mechanics. Now about the Dr. Arun Kamble. So he holds a PhD from IIT Bombay, and he has completed MTech from the IIT Kanpur, and he has recently completed his postdoctoral research in finite element modeling at the IIT Bombay, and he has worked extensively on the numerical modeling of the advanced materials using the tools like ABAQUS and ANSYS. So with this short introduction, I would invite Dr. Kamble to take the session, take the charge from here. So thank you to all of you for joining this session.
Okay, thank you,
Sarva,
Pratyush. Nice introduction. So, can I start now, or we have to wait for some minutes?
No, you can start now.
Okay. Oh, there are people who are joining now only.
Anyway, it's
So,
recorded, so you can start
okay,
it now.
okay. So, welcome to all to this course on Introduction to the Finite Element Analysis and their implementation in the ABAQUS. So first I will I have divided this session into two parts. First, I will give the theoretical background related to the finite element analysis, and then I will show you the how we can solve one problem in the ABAQUS, means by using this theoretical approach, or we will see some demo on the ABAQUS. So let us start. So my name is Dr. Arun Kamble, and this is my educational background. So so to understand this course in in detail, you need some prerequisite. First, one is the numerical methods. I think in your UG you have studied all these prerequisites. I assume that. So numerical method is first one. Second one is the matrix operation. Third one is the calculus, and the fourth one is a differential equation, and the concept of the linear algebra. So I will start with the history, present, and future of this finite element analysis. So first, in 1906, civil engineering applications using 1D beam analysis uh, was performed, and then in 1909, Ritz introduced the variational methods. So in the finite element analysis, there are different methods. We are going to see that variational approach or direct method or weighted residual method that is generally used to solve the steepness matrices, and the formulation of that is already was already done by some of the scientists, Ritz, Galersin, Courant, and this pressure range. Okay, all this. And in from the if you see here in the from the 1990s, low cost powerful PC workstations. which enabled this finite element analysis used in the mid and small scale industries. So this is a growth in FEA publications in terms of the papers. So from the 2006, if you see, there are infinite papers on this subject. So the present status is that this subject is generally divided into two parts. So in the UG level, there is a theory subject which focuses on the derivation of the stiffness matrices and the assembly of the uh, stiffness matrices, and there is a solution techniques. So that is a theoretical finite element analysis. And in the practical applications, by using various commercial tools, we can design a new product, then cost optimization and the failure analysis. And there are other some applications are also there. And so here I will explain what is the theoretical FEA and the software-based FEA. So in the theoretical finite element analysis, we the main aim is to find the stiffness matrices. Okay. So here the core component of the FES we consider is that the geometry and the material properties. So as you know that stiffness is generally defined as the force required for the unit displacement F by D. And there are various methods to derive the stiffness matrices. First one is the direct method. Uh, that is easy to understand, but hard to program. And second one is the variational method, which is generally called Rayleigh-Ritz method, which is moderate for the coding and the but it is complex in theory. And third one is the weighted residual method, which is generally also called as the Galerkin. Means in FEA we generally use the Galerkin weighted residual method, and it is a complex, but we use widely in commercial softwares. So the examples of the stiffness means we can there is one example to correlate the stiffness of material, the steel versus aluminum rods. So if you means if you see here, the steel is steeper due to the higher elastic modular. So so this is one example, and second one is a finite element software based workflow. So in this, there are three steps: pre-processing, solution phase, and third one is the post-processing. So in the pre-processing phase, we do the solid modeling, and then the meshing, and we apply the boundary conditions. And in the solution phase, we solve the mathematical equations, and then in the post-processing, we interpret the results and which their post-processing. So generally, the typical design process that we follow in the industries. First one is we define the problems. We define the problem, and then we synthesis. So synthesis means here synthesis. It is an act of combining elements or new things to form various things to form something new. So this is a synthesis. And then third one is the modeling and the formulation. So here we model our problem, model the here we model the by using the commercial design softwares, model our problems by using CAD softwares, computer aided design, and then we analysis by using CA. Means here analysis is related to the CA, computer aided engineering, that we generally use software such as ABAQUS and SIS like this. And then we evaluate our results or cross check our results. If it is means uh, the results are good as per our expectation, then we go for the prototype. Otherwise, we again means go to the say the synthesis steps. So and this and next after the prototype design, we test the prototype and prototype, and if any modification, we again go to the synthesis phase, and then if it is okay, then we go for the final design, and then manufacturing, and then marketing, and we provide the products to the end user. So this is a typical design procedure we generally follow in the various means in the industries. So in this typical design process, so this process means modeling and formulation, analysis, and the cross-checking, evaluation and cross-checking is generally related to this finite element analysis. Okay, So this is the finite element analysis. In engineering, generally we formulate our problems, or we represent the given physical system in terms of the mathematical models. And these mathematical models are differential equations with a set of the corresponding boundary and initial conditions. Okay, and for that means to solve the mathematical models, we generally use we generally use the analytical solutions, and which is generally composed of the two parts. First one is the homogeneous part, which shows the natural behavior of the structure, and second one is the particular part, which shows the disturbance solutions or the to the external forces. Means this is in case of the, if you see the homogeneous equation, differential equation, you will give the homogeneous solution, and non-homogeneous differential equation will give the homogeneous plus means homogeneous plus the particular integral solution. So there are many practical engineering problems for which we can't get the exact solution. Means analytical solution means the exact solution, but in the practical engineering problems, very complicated in shape and size, for that we can't get the exact solutions, and we generally use the numerical solutions. But numerical solutions are not exact. And in typical case, if possible, exact solution are only at discrete points. More, for example, we can find the exact solutions at some discrete points, which is generally called nodes. And therefore, the first step of the any numerical procedure is discretization. Means in when you use the numerical solution to solve any problems in the engineering, we first use the discretization. We divide the problem into number of domains, and means or the divide the material into number of small subregions and the nodes. Okay, that way we do the discretization. So let us see some of the methods. Means there are three methods only to solve any engineering problems. So first one is the analytical method. So first one is the analytical method, second one is the numerical method, and third one is the experimental method. So the analytical method, it is a classical approach. Okay, classical approach, it is only applicable for to solve some simple problems such as cantilever beam or the bar problems. Okay, for that class means the exact solution is available. Means analytical solution gives the exact solution. That's why it is called as classical approach, and which is a 100% accurate result, which gives the 100% accurate results. And also the results are a closed form solution. It gives the closed form solutions. And second one is a numerical method. So it uses the mathematical representation of the given physical system, but this is a approximate, and we made a lot of assumptions in this method. But here the prototype is not required, and we can solve the real life complicated problems. So the results, we can also verify the results by the experimental results. And third one is the experimental method. So it gives the actual behavior of the system, but here the time and cost consuming. But this is the time and cost consuming method. Here we need a prototype to test, and we need to test minimum 2 to 3 prototypes in order to get exact results. So in the engineering, the numerical methods means this numerical methods is generally classified into these 4 types. First one is the finite element method, which is generally applicable for the linear, non-linear buckling, thermal, dynamic, and fatigue analysis. And the second one is the boundary element method. So as the name suggests, it's only consider the boundary of the problem, and it is generally used to solve the acoustic or NVH problems. NVH means noise, vibration, and harshness. And third one is the finite volume method. So it depends on the Navier-Stokes equations, and it is generally used in the computational fluid dynamics (CFD) or the computational electromagnetics. And the last one is the finite difference method. So it only consider the the results at the nodal point, and it is generally applicable for the thermal and fluid flow analysis. in combination with this finite volume method. So what is the human limitations? There is one limitations of the human that to grasp the behavior of the complex surrounding, and therefore there are different there is one method to determine the behavior of such behavior of the complex system. So in this, first we discretize any complex systems. Means first step is a discretization. Here we divide the systems into small numbers of subsystems or elements, and then we analyze elemental systems under different loading conditions and the environment. And after that, we assemble. Means we use the we use in the assembly step. We combine all the elemental solutions into complete system, and then we determine the complete behavior of the system. So what is FEM? So it is a computational approach. Finite element method. It is a computational approach for solving problems governed by the differential equations. So you can see there are some applications. So we can use this method to solve the problems in the solids and structural mechanics, aerospace, in the aerospace, electronic devices, automotive, nuclear. Also, we can use in the fluid flow analysis, heat transfer analysis, and in the environmental sciences, electromagnetics, acoustic, biomechanics, geomechanics, seismic analysis. All these are the applications of these methods, quantum mechanics, and also we can use in the coupled physics problems, or for example, in fluid structure interactions. So let us see what is this the definition of this finite element method. So it is a numerical method of solving systems of partial differential equations. Okay, so in this method, this PD partial differential equations means PD systems. We reduces these PDF systems to systems of algebraic equations, and that can be solved using the traditional linear algebra techniques. So these are some of the applications in the heat conduction, means heat transfer problems, structural mechanics, and the electromagnetic problems. We can use this method. So in this method, we model the physical system first. So this is the one model physical system. This is the one physical system of the vehicle, and this is the axle. So here we can. This is the equivalent beam model for this axle, and this is a static model. And you can also think static model is means with respect to time it is constant, but in the dynamic case we need to consider the effect of the time. So in this method there are different types of analysis we can perform. First one is static analysis. In this we can do the displacement. We can in the structural uh, analysis we can find the displacement. We can do the stress analysis, we can do the rigidity analysis, or in case of the thermal analysis, we can also find the thermal temperature distributions in the problems. And then in the dynamic analysis, we can perform the structural analysis here. And in this, we perform the vibration analysis, fatigue fracture analysis. We can also do the creep analysis, acoustic analysis, or in case of the this thermal dynamic analysis, we can perform just transient analysis. In the motion analysis, we can find the velocity and acceleration, or that is a kinematic analysis. We can perform the motion dynamics and the multibody dynamics also. And we can optimize weight, size, topography, and constraint by using this method. So what is computational mechanics? Next concept is of computational mechanics. So it is a mature field that addresses the development of the numerical methods for the solutions of the problems in the mechanics. So it is generally related to solids and fluids. So these are the common computational mechanics methods. First one is this finite difference method. Then finite volume method, finite element methods, and boundary element methods, spectral methods, mesh-free methods, and many more. So all these methods comes under the category of the computational mechanics. So now we will see the exact definition of this FEM word by word. So it is a numerical method, and it gives the mathematical representation of the actual problems, and but it is an approximate method. Okay, it is a numerical which is an approximate method. So what is the word this finite meaning? Okay, so consider this is one domain which consists of the number of which is made of the number of atoms. Okay, generally any systems which is made of the atoms. So you can see there are a few points here. Means in the material we can see we can consider this is a as the small number. The small point means it is a one atom. So we can see it is a number of points here is the infinite. And in general, for any point or any system, the degrees of freedom per point is 6, means 3 translational and 3 rotation. 3 translational means there is a translation in x, y, and z direction, and rotation about this x-axis, y-axis, and z-axis. So therefore the total degree of freedom per point is 6, and therefore when we multiply this total number of points multiply by 6, you will get also the infinite number of equations. Infinite number of equations. So here, when we solve this domain or the system for the infinite number of equations, so it is impossible. We can't solve the infinite number of equations in its true form. Therefore, it is impossible. Therefore, we divide this domain into uh, number by using the elements and the nodes. Okay, here you see we can connect these points. We can consider this point as a node, and we can connect these nodes by using this element. So here there are total number of nodes is only 8, and the degrees of freedom per node is 6. Okay, so therefore the total equation will be 48. So here we have to solve only 48 equations. So the word finite meaning is that so any continuous object has infinite number of degrees of freedom. Okay, which is impossible to solve in its true form. And therefore, this finite element method allows such a problem to solve by reducing this degrees of freedom from infinite to finite. Clear? So this is the meaning of this word finite. Means here it is related to the degrees of freedom, and as here means any continuous object has infinite number of degrees of freedom, and therefore we convert in this method we convert this infinite number of degrees of freedom into the finite element degrees of freedom problem. So this is the meaning of this word finite. Next is the element. So this is achieved, this conversion from the infinite degrees of freedom to the finite degrees of freedom is achieved by discretizing a body into a finite number of parts, which is called elements. So therefore the second word element is related to this. It is related to the finite number of parts. And these elements which have connective points, which is called as nodes. So therefore, all the calculations is based on these points, which has been defined by a interpolation functions. Means generally in finite element analysis, we first calculate our unknown variables, unknown quantity at nodes, and then we interpolate that unknown quantities to find any value inside the element. Okay, and that is mm, uh, miss, that is using the interpolation function or the shape function. Means what is the meaning of shape function? Means when shape function is used to find the unknown variables inside the element by using the nodal values. Okay, nodal values. So this is a shape function which also gives the value of a field variable within a element. So this is the meaning of this term word element. And third one is the method. So this method word is related to the stiffness matrix. Method means there are various methods in the finite element analysis or the finite element method to derive the stiffness matrix of the element. So there are three methods we generally study. First one is the direct method, second one is the variational method, and third one is a weighted residual method. Okay. So the procedure is that means the typical procedure we are going to see now of the finite element analysis. So this is a typical, these are the typical steps in the finite element analysis. First, we create the mesh. Okay, we create the mesh. In this, we grid of the nodes and the elements. By using the grids of the nodes and the elements, we create the mesh that represent our physical model, or that may represent our physical system. And then we, after creating the mesh, we apply the nodes. and then we define the boundary conditions which prevent the model from the moving, and then we define the element properties, means the Young's modulus, Poisson's ratio, all the plasticity related data in case of the structural analysis. Then we define the element properties, and then all these steps are related to the pre-processing. And the second one is the solution phase. So in this, we assemble the element stiffness matrices. Then we solve the systems of the linearly observed equations, and then we calculate the stresses in case of the structure.
Arun, you have unmuted.
Hello, am I audible now?
Yes, Arun, you are audible now.
Okay, okay, thank you. Okay, now we are going to see one case study. Here we are finding the deflection of the bar under axial loading by using the finite element procedure. So here you can see here, if we fix the left end of the bar with the constant cross sections, its end deflection is given by this formula. Means I think in the solid mechanics or the strength of material subject, we have seen that the deflection of the bar or the deformation bar in terms of this means this is the formula for that to find the deflection of the bar, which is equal to PL by AE. PL is the load at this free end. L is the length of the bar. A is the cross-sectional area, and E is the Young's modulus. So in the finite element analysis, we first do the modeling, okay, or the meshing. So here um, we divide the domain into three subdomains of each having area A, Young's modulus E, and length L. Small L is the length of each element. So there are three elements and four nodes. So here this is a 1D problem, and the each node is having 1 degrees of freedom. Okay, that is displacement. So displacement in this x direction. Now separate this the element from complete domain and draw the free body diagram. Okay, so here we are going to see the methods. Means this we are going to solve. We are solving this problem by using the direct approach. Okay, means to understand the basic procedure of the finite element analysis. So here first step is to separate the element from the complete domain and draw free body diagram. Okay, so this is the separate means element from that assembly, and you can see the I and I plus 1 are the global coordinates, and this 1 and 2 is mm, wait a minute. This 1 and 2 are the local coordinates. Okay, and U1 is a displacement at this U1 is a displacement at this point at this node, and U2 is a displacement at this node. Okay, and F1 is a force at this first node, and F2 is the displacement at this second node. So here we can apply the Newton's law. Newton's law means force is equal to summation all the forces equal to 0. So
Adam. हेलो अरुण भाई, क्या हो गया?
नहीं, मैं तो चालू है मेरा।
नहीं, यहाँ पे नहीं आ रहा है।
एक मिनट, फिर से ज्वाइन करो क्या?
फिर से ज्वाइन करो।
कब से कहाँ से डिस्कंटिन्यू हो गया?
वही जो 1 डिग्री फ्रीडम से था, जो कैंटिलीवर बीम वाला फार्मूला लगाए थे, वहीं से।
ओके, मैं फिर से ज्वाइन करता हूँ।
सर 19 नंबर पे डिस्कंटिन्यू हो गया।
पता नहीं, दोबारा करो।
Hello, Pratyush. Am I audible now? Hello, Pratyush.
Yes, now you are audible.
Okay, let me share my screen.
Yes.
Is it visible? Presentation?
Yes, yes, yes. So you should start from the formula that.
Okay,
Yeah,
so I will
this.
start from the case study here.
Yes,
Is it okay?
yes, yes. So,
Okay, so guys, here we are going to see one case study to find the deflection of the bar under axial load. So here we are considering one bar which is fixed at left end and the free at one other end, right end. So the free means there is a force P at the right end, and here we are finding the deflection by using the finite element approach. Okay, so in the strength of material we have seen that we can find the deflection by using this formula PL by A. Okay, L is the length of this total length, A is the cross-sectional area, and E is the Young's modulus. First step is to divide the domain into three domains. You can use many numbers of elements, but I think for this problem, this is simple problems. Three is enough. So the first step is to divide the domain into three subdomains, each having area A, Young's modulus E, and length L. So each node is having 1 degrees of freedom. Here, 1 degrees of freedom, that is a displacement. Now separate the element from the complete domain and drop free body diagram. So by using the Newton's law, summation F is equal to 0. So we can find the equations corresponding to the node number 1 and the node number 2. Means we can apply the summation F is equal to 0 at node number 1 here and node number 2. So F1 is the force at node 2 and F2 is the force at node number 2. U1 is the displacement at node 1 and U2 is the displacement at node 2. So these are the equations, equilibrium equations. So we can write these equilibrium equations in the matrix form. So this is the equilibrium equation in matrix form, and here. So this is the stiffness matrix, which is consist of the this element properties A, element and material properties A by L into 1 minus 1 minus 1 1, and this U1 U2 is the displacement vector, and F1 F2 is the force vector. So now next step is to construct the element matrices for each element. So by using this approach, we can construct the element stiffness matrix for the element number 2 and element number 3 also. Okay, so these are the element stiffness matrices for element number 1, element number 2, and element number 3. So now next step is to assemble this element stiffness matrix into global form. So in the assembly process, means we have to first write the node numbers in the horizontal direction and the vertical directions. So this problem consists of the 4 nodes, 1, 2, 3, 4, and each node is having 1 degrees of freedom. So in so you have to write the element number element values to the respective elemental place. Means here, if you see here, this is this is a 2 by 2 matrix corresponding to the node number 1. Therefore, this is the K11. This is the K112. This is the K13 12. This is the K11. This is the K12. Means first row, first column. This is the first row, second column. Means K11, K12, K21, and K22. So here also you have to write this K11 here, K11. So it will be 1 1, and here you can write K1. K1, K12 here, minus 2, minus 1. Here also you can write this minus 1, which is related to the K21, and here this 1 is related to the K22, and from this second element you will also get one value K. This is also related to the K22. So here you can add. Similarly, you can do this assembly for all the element places. Okay, matrix places. So this is a global, this AE by L into this 4 by 4 matrix is called as global stiffness matrix. And this is the global displacement vector U1, U2, U3, U4. And this is the force vector F1, global force vector F1, F2, F3, F4. F1 is the force at node, F2 at node 2, and F3 at node 3, and F4 at node 4. So here you can see this is this A by L is the system properties, and this one is the global stiffness matrix. This is a global displacement vector, and this is a global force vector. Now, after formulating this system equations in the global form, we can apply the boundary conditions to this FEM model. So what are the boundary conditions here? So at the left end, displacement at fixed end is 0. Means left end is fixed, therefore displacement is 0. So U1 is 0 here. This U1 is 0. And at right end or at free end, force is applied. That is F4 is equal to P. Okay, so write down here U1 is equal to 0 and F4 is equal to P. Okay, then uh, here you can see here the internal force applied by is balanced by the externally applied force. Therefore, this F2 and F3 are also 0. Okay, it is balanced by the externally applied force, this Fp. Therefore, the total unknown quantities are total unknowns are 4 only: U2, U3, U4, and this reaction at this node number 1. Okay, so there are 4 equations and 4 unknowns. U1 is 0. We have to find the U2, U3, U4, and this R reaction. Okay, so there are 4 simultaneous equations with 4 unknowns. And we can here to solve these equations, these systems of equations, we can use Gauss elimination method. So this is in terms of matrix form, we can write AE by L into stiffness matrix, global stiffness matrix into displacement vector is equal to force vector. So we can simplify this equation and find the values of this. We can write the U in terms of this K inverse and this force vector, global step, and the solution of this gives the displacement of this node number 2, 3, and 4. So, and the reaction. So how to determine the stresses and strain by using this displacement? So once we know the deflections, we can calculate the strain for each element. And for the one-dimensional problem, we know the formula for the strain, which is equal to du by dx, change in length upon original length. And for our bar problem, we can write its strain, which is equal to elemental strain, which is equal to U2 minus U1 divided by L. And this is the formula for the yield stress. Sigma is equal to E into epsilon for the one-dimensional problem. And this is a force. We can calculate this force in each bar can be calculated by this formula. F is equal to sigma into A. Substitute here the value of this sigma, which is equal to AE in terms of U2 minus U1 divided by L. So this is the typical finite element states by using the direct method. So now let us see the difference between the finite element and the classical method. So in the classical method, means for example in the analytical method, means exact equations are formed and we get the exact solutions. Okay, but in the finite element analysis, we form the exact equations, but we get the approximate solutions because of the this meshing. Means we use the elements and the nodes. And the solution have been obtained for the few standard cases, but in the finite element method, we can get the exact solutions for the standard cases. For example, the cantilever beam bar problem. For that, the analytical solution is also available. For that case, we can get the exact solutions. But whereas the solution can be obtained for all problems by using the finite element analysis. Okay, means by using the analytical approach, we can't get the solution for all the problems. All the simple, we can get a solution for the simple problems, but for the complicated problems, we can't get the solutions by the analytical methods. But by using the finite element analysis, we can get the solution for any problems. And also, the classical method is difficult to incorporate this following complexities. First one is the shape, boundary conditions, and the loadings. But the finite element method, in the finite element method, we consider the problem as it is. So I think this is not important for you now. So these are the some of there are some of the finite element packages, finite element analysis packages, ANSYS, ABAQUS, Nastran, LHDyna, Adina. These are the the ANSYS and ABAQUS is mostly used. ABAQUS is mostly used in the universities, and ANSYS is mostly used in the industries. So we have to remember some of the points in order to use the finite element analysis packages properly. So, okay, so the some of the points are that first one is the which elements are element types. Hello.
Actually, no, Arun, that was noise.
Okay, am I audible now, Pratyush?
Yeah, you are audible. But that was noise, so ignore that.
That was
Some noise from the audience, so please ignore that.
okay, okay, okay. Okay, please mute that. If you have any question, then in between, means after the end of presentation, you can ask. Okay.
Okay.
So here means first point is to you have to remember is that which element types are to be used for solving the problem. Then second one is to how to discretize how to do discretize or how to mesh to get the good results. Then how to introduce the boundary conditions properly, and then how we can develop the material properties or the element properties and what are their limitations, and how to display our results pre-processing after the means pre and post processing results, and also to understand their limitations, and last one is to understand the difficulties involved in the development of these FEM programs. Okay, means for example, for the simple means for the common materials, the material models are also available generally in all these commercial packages. And if you want to use some material models for the any new materials, then we have to develop our own code. Okay, so that there are some of the limit difficulties related to this uh, FEA packages, and hence the need for this the checking commercially available packages with the results of the standard cases. So this is the introduction of the finite element analysis. So now we are going to see in briefly the various types of analysis that we can perform in by using this finite element analysis. Okay, so so this finite element analysis is related to the CAE, means term CAE. Okay, in the industry we generally refer the finite element analysis as a related to the CAE, that is a computer aided engineering. So which includes following types of analysis. Okay, so in CAE, first we do the linear static analysis. Second one is the non-linear analysis. Third one is the dynamic analysis. The next one is the buckling analysis, thermal analysis, fatigue analysis, optimization, CFD analysis, crash analysis, and last one is a NVH, noise, vibration, and harshness analysis. Means all these types of analysis we can perform by using this method, finite element method. Okay, so let us see briefly all these types of analysis. First one is the linear static analysis. So here the word linear means straight line. Okay. So in strength of material, we use the formula called means related to the stress, which is equal to sigma is equal to E into epsilon or E into epsilon. Okay, and which is the equation of the straight line. So if you see here this diagram here, you see here this plot stress versus strain. So you can see the slope of this straight line is uh, stress versus stress by strain. Okay. So here the equation of this is the is sigma is equal to E into epsilon is the equation of the straight line and passing through this origin E origin, and here the E is the Young's modulus, which is the slope of this curve, and it which is a constant. Okay, but in the real life, after crossing yield point, the material follows non-linear curve. Means I think we have studied the stress strain curve, and this is for the standard low carbon steel. So in the real life, after crossing this yield point, material follows a non-linear curve, but software follows this path. Okay, for linear static calculations, straight line path. And in the software, the means in the real life, component breaks into two separate pieces after crossing this ultimate stress. But in the software's based analysis, we can't get this breaking phenomena. We can't see the breaking phenomena. Okay, means software-based analysis never show failure in this fashion. So it shows a single unbroken part with red color zone at the location of the failure. Okay, in the software we can only see the when we model the failure means we use the in case of the damage modeling means when we use the damage model and the failure or failure criteria, then for that case we can see there are two parts which are which have broke, but in general in the linear static analysis we can't uh, get the to a separate part, but it shows the single unbroken part with a red color zone at the location of the failure. And therefore, and the last one is the researcher has to conclude whether the component is safe or failed by comparing the maximum stress value with the maximum stress in the analysis versus the yield or the ultimate stress value. So this is the linear static analysis. So in this, if you see this plot, F versus T. So here df by dt is 0. It means the force is static. Okay, that is no variation with respect to for time. You can see in the linear static analysis, this force is static, no variation with respect to time. And in this, we can use the equilibrium conditions or the equilibrium three equation the equilibrium conditions summation fx, fy, and fz, which is equal to 0, and the three equilibrium conditions related to the moment summation mx, summation my, and summation mz is equal to 0. So all this finite element model fulfills this condition at each and every node. And for the complete model summations of external forces and moment is equal to the reaction forces and moments. So what is the practical application of this linear static analysis? So it is the most commonly used analysis. So all the aerospace, automobile, offshore, and civil engineering industries perform linear analysis. So these are some of the commonly used softwares: ABAQUS, ANSYS, Nastran, and many more. So the second one is a non-linear analysis. Non-linear analysis. So here the force versus displacement or the stress versus strain curve is non-linear, okay, or polynomial. And here the steepness is the function of the displacement d for the linear analysis means here the steepness is the function of the displacement, okay, d. But in the linear analysis, in the previous slides, for the linear static analysis, displacement is a function. This means k is the stiffness matrix is a constant, and it is independent of the displacement. Okay, so in general, in the engineering, uh, we study, or in the finite element analysis, we analyze only three types of non-linearities. First one is the geometric non-linearities. So in this, what is the geometric non-linearities? Here, the stiffness changes due to the geometric deformation. Okay, stiffness changes due to the geometric deformations. The first example of the geometric nonlinearity is large strain. So you can see here the element are undergoing large displacement. It means if an element shape changes, its individual element stiffness will also change. Second example is large rotation. So in this, if an element's orientation changes or it rotates, the transformation of its local stiffness into global components will change. Okay, and third one is the stress stiffening. Okay, so this is another example of the geometric nonlinearities. So it is associated with the tension bending coupling. This tension bending coupling. So you can see you can consider this is as a membrane. So the more the tension in the member, the more its bending rigidity or the stiffness. So here the stiffness is also changing. And the last example is spin softening. So this is the phenomena relating to the stiffness change due to the rotational speed of the components. For example, one example is of the spin softening is that in a brake dynamometer we can observe this type of non-linearities. There the stiffness of the belt is changed. Second one is the material nonlinearities. So in this stress strain relation is nonlinear. So you can see in this plot, stress versus strain plot. This relation is nonlinear. Okay, up to this it is linear, and in case of the elastic plastic material, it is nonlinear. Okay, and here also for the nonlinear elastic material and for the hypervelocity elastic material, it is nonlinear. Okay, so these are some of the examples of the material nonlinearities. And third one is the contact nonlinearities. So it changes the boundary conditions due to the loading. Okay, so here you can see in this figure, the boundary conditions is changing. So after this delta displacement, change in boundary condition at node A will occur at a nodal displacement of the of delta. So this is an example of the contact nonlinearities. So all these types of nonlinearities we can model or analysis by in the nonlinear analysis. Okay. Third one is the dynamic analysis. So dynamic analysis or the vibration analysis. So this analysis is generally divided into free and forced vibration. First one is in free vibration or the free dynamic analysis. We find the natural frequencies. So we know the natural frequency means it is the frequency with which any object will vibrate if disturbed and allowed to vibrate on its own without any external force. So there is a formula to find the natural frequency of any system, which is equal to under root k by m. K is the stiffness and mass, m is the mass. Okay. So by using this, we can find the natural frequency of any system. And second one is the forced vibration. So in this, we consider the response to the external excitation. But in the free vibration, there is an initial excitation only, and therefore the external force is zero. But in the force vibration, we consider we find the response to the external excitation. So there are three different types of this forced vibration. In this first one is we do the frequency. We find the frequency response. So in this, we study the problem in the frequency domain, and steady state means we find the steady state sinusoidal excitations. But this frequency response analysis is limited to the linear elastic structures. For example, rotating machinery, unbalanced tires, and helicopter blades. And second one is a transient response. So this is this performs this response is we found this response in time domain, and we use arbitrary but well-defined excitations and the constant acceleration or force at a given frequency. For example, in case of the road excitations, we can use this type of analysis. And third one is the random vibrations. So these vibrations are random in nature of loading, and usually the form of PSD. The application is in the input. We use in the input in the form of PSD, power spectral density. And this is the general equation of motion in the dynamic analysis. It consists of the mass matrix. This is the damping matrix, and this is the stiffness matrix. And this x double dot is the acceleration, x dot is the velocity, and x is the displacement, and f of t is the external force, which is a function of time. Okay, so from this equation of motion, dynamic equation of motion, we can do various types of analysis when we make this acceleration terms. Okay, mx double dot is equal to 0, and this damping terms is related to 0. C into x double dot is equal to 0, and there are only these terms kx, which is equal to f, and where the k and f of t is a constant. Then this type of analysis is linear static analysis. And when this acceleration term and the velocity term is 0, and if this k is a function of this displacement f, displacement k is a function of displacement, and this force is constant, then it is called as non-linear static analysis. And third one is when this external force is 0, damping force is 0, and there is only mass and stiffness matrix is 0, or there is the effect of the mass and stiffness only, which is equal to constant, then that is considered as a free vibration problem. And if all the terms are present in this above equations, then this is considered as a forced vibration problem. So the practical applications of this and dynamic analysis are to find the uh, natural frequencies and the mode shapes. So in case of the free vibration, and in case of the forced vibrations, we can means it is applicable for the components subjected to force, displacement, velocity, accelerations, varying with respect to time and frequency. So these are some of the commonly used softwares: Nastran, ANSYS, ABAQUS, MATLAB. Okay, we can perform dynamic analysis by using this commercial available softwares. Fourth one is a linear buckling analysis. So we can also do the buckling analysis by using this FEM, by using this method. So it is applicable only for the compressive load and slender beams and sheet metal parts. It is applicable. So here the bending stiffness is very less than the axial stiffness for the buckling problem. And here we can see the large lateral deformations. And we find generally the output from the software we get, that is the critical value of the load, is the failure value at which this material is buckling. So these are the commonly used, the applications are the commonly used for the civil engineering applications. For example, in case of vacuum vessels, long gear shifting rod analysis, etc. And these are the commonly used softwares, ANSYS, ABAQUS, Nostran, etc. Then we can also perform the thermal analysis by using the finite element method. So in the thermal analysis, means thermal or the heat transfer problem, we know the various modes of the heat transfer: conduction, convection, and the radiation. So we can do the 1D, 2D, 3D steady state conduction analysis, or the 1D, 2D, 3D unsteady state conduction analysis. Or we can also perform the natural convection analysis and the forced convection analysis. Or we can do and also we can perform the radiation analysis, for example, the spectral radiation and the diffuse radiation. So these are some of the practical applications in case of the engine, radiator, exhaust system, heat exchangers, power plants, or in case of the satellite design, we can also use this thermal analysis. So these are some of the commonly used softwares. So next type of analysis is the fatigue analysis. So the calculation for the life of the structure when subjected to the repetitive load is called as fatigue. So here we use software use the SN curve. SN means the alternating stress versus cycles. N means cycles. S is the alternating stress. Or this E versus epsilon versus N, alternating strain versus reversal, is the base for this particular fatigue calculations. Like means in the static analysis we use the stress versus strain, sigma versus this epsilon. In similar way, we use the SN curve in the fatigue analysis. Static and dynamic analysis cannot tell us how long the component will survive for the given load, and there is a no consideration of factor like surface finish, heat treatment, decarbonizing, these real alloying elements, or the representation of the spot and arc weights. Therefore, in all these factors we consider in the fatigue analysis. So this is the SN curve, low related to the low cycle fatigue and high cycle fatigue. So the practical application of this fatigue analysis are, it is applicable to all the commercially components subject to the dynamic loading. And for example, in case of the automobile components, we can use this fatigue analysis. And these are some of the commonly used softwares that we can, by using these commercially available softwares, we can do the fatigue analysis. The next one is the optimization. So generally there are two types of optimization: geometrical means optimization for the geometry parameters, and second one is related to the shape optimizations. Here this geometrical means optimization for the geometry parameters works well at the individual component level rather than the complicated assemblies. But it is the shape optimization usually restricted to only linear, static, and non-normal modes dynamics. And the software here, the softwares can not add or remove geometry on its own, but can play with the only predefined parameters within the specified limits. And this is in the shape optimization, software can give good hint for the addition or removal of the geometry. So these are some of the applications applicable to any component which is over or under design. And these are some of the commonly used softwares: OptiStruct, Tosca, Nastran, and ANSYS. Next one is the computational fluid dynamics. It is in this fluid is substance that continuously deforms under an applied shear stress, regardless of the magnitude of the applied stress. Here, the gas and liquid both are fluid. Means generally in the fluid mechanics we study the fluid statics, which is related to hydrostatics, and the fluid dynamics. In fluid statics, we study the fluid at rest. It is easy from the calculation point of view, and here there is no variation with respect to time. We can use the fluid static approach in case of the dam design. And in the fluid dynamics is the study of the fluid in motion. Here the calculations are more complex. Variation with respect to time is considered. Here we can get the nonlinear equations applicable in the aerospace, automobiles, and walls. So all this computational fluid dynamics, means this CFD is a branch of the fluid mechanics which uses the numerical methods to analyze the fluid dynamics problems. And generally it is based on this Navier-Stokes equations, which is related to the mass, momentum, and energy conservation equilibrium equations. So these are some of the practical examples, applications: drag predictions and the streamlining of the car, combustion chamber design to then optimum fuel air mixing, or in case of aeroplane design, we can also use this CFD analysis. So these are some of the softwares: Fluent, Star CD, CFX, and the CFD expert. Then last one is crash analysis. So here we can uh, do the structural crash worthiness or the full dynamic or the impact simulations. So generally the crash analysis is performed in the explicit domain. Okay, explicit analysis. So, and second one is the drop test simulations. So here the drop test is free fall test used to verify the structural integrity of the component. For example, the black box of the aircraft, mobile phones, consumer goods such as TV, fridge. Okay, in that case, we can use this drop test simulations. Okay, this is also performed in the explicit domain. And the next one is the occupant safety, which evaluate the crash effects on the human body and ensure safety of the driver and passenger. So these are some of the commonly used softwares: ArrestDyna, PAMCrash, Radios, ABAQUS Explicit, or the MADAMO, etc. There is the last one: noise, vibration, and harshness. So the practical application means here we can predict how much sound pressure level is felt by the vibrating source at a certain distance as a function of the solid angle, which is related to the sound radiation or the scattering problems. So here the solution method is boundary element methods, because as the name suggests, it only considers the boundary of the problem. And second one is the coupled or vibroacoustic problems. So the examples are we can analyze the noise level felt at the driver's right here due to the engine vibrations in idle conditions. So in this case, we can use the finite element methods. So these are there are some practical applications. First one is the computing the sound pressure levels in automobiles, or we can use this analysis in aerospace designers as the customers, which always prepares low noise levels. And these are some of the commonly used softwares: Sysnoise, LMS, Virtual Lab, or we can also use the MATLAB. Okay, for such type of for noise, vibration, and harshness analysis. Okay, so these are some of the types of analysis that we generally study by using this finite element analysis approach. Okay, so now I will give one small demo by using the ABAQUS. How we can solve uh, one simple problem by using the ABAQUS software, which is commercially available. I think have you installed this software in your machine?
Yes, Arun. I think they have installed because I have already given them instruction.
Okay, okay. So I think I will give a step-by-step process for one simple problems. There we can see the the procedure of the modeling and how we define the boundary conditions, loading conditions, and how we solve the problem that I will give. So let us see. So when we open the Abacus window, okay, you will get you will see this this window. So these are the this is in this you will see the component of the main windows of the Abacus, or it is called it is related to the CA Abacus CA windows window. Okay, so this is the title bar. I think click on this, open the Abacus CA. Go to this here, go here and click on this Abacus CA. So before proceeding to the demo lecture, you can ask me any questions related to the theoretical finite element analysis. If you have any doubts, we can discuss.
So I
Okay.
would suggest everyone to just do practice with Arun also. Just don't watch the session.
Wait a minute. Wait
Do
a minute. Can you? Hello, Pratyush.
yes,
Can you
yes.
speak now?
So I was saying that means I was requesting everyone to just do the practice as you were showing your screen. Yes. So I was just suggesting. Yes, Arun, you can start.
Okay. So I think at the end of this demo lecture also we can discuss some of your doubts.
Yes.
Okay. So first go to the Abacus CA. Open this Abacus CA here from here. Open. Okay. Open the Abacus CA from your laptop or machine. Click on that. So you will get this window. Wait for some time and to open the Abacus. Okay. Before that, I will give the problem description. So after opening the Abacus CA, so you will see this window. Okay. So in this, the first one is this is the title bar. This is the menu bar. This file, model, viewport, view is related to the menu bar. And then all this one is the toolbar. Here from this you can, this is the related to the, this symbol is related to the toolbars. And this is the context bar. So you can add more tools in this context bar also. And this one is the model. Okay, let me this is the model tree. This is a toolbox. From this, you can select any tool. This is the viewport. Okay, so in the viewport, we create the CAD model, or we see the results, or we do the meshing in the viewport. And this is a prompt. So here you will get the message after clicking any tool. And this is the message area. Okay, this is the message area, and this is the prompt command. So from this, you can also perform the operation. So first I will explain the detailed procedure of the Abacus. So in the Abacus, there are different models. So here you can see there are different models. Part module. First one is the part module. Second one is the property module. Third one is the assembly. Next one is the step module. Interaction, load, mesh, optimization. Then job module. Then visualization module. And then last one is the sketch module. So in the part module, we create the part. Okay, first model is the part. So we create the part or we import the part. Okay, we import the CAD geometry. Okay, from suppose your CAD geometry is from the CATIA or the SolidWorks. So either we import the CAD geometry or we create the this geometry in the part model. Second model is related to the property. Okay, which creates the material. The property model which creates the material or which create the section also, and we assign that section to that part created in the part model. Okay. So third model is assembly. In this, we create the assembly of the various parts that we have created in the part model. And next one is the step model. So in this, we define the analysis type. In interaction model, we define the how different parts interact within an assembly. If there is only one part, then we can skip this interaction model. If there are 2 and 3 parts, we have to use this interaction model also. Then load model, in the load model, we define the loads and the boundary conditions. Okay. And next model is mesh. So in this mesh model, we create the meshing. Okay, mesh by using nodes, by using various types of elements. And the next model is job. In this, we run the analysis. And in the visualization model, we view the results and post-process our results. So this is that these are the different models that we use. And step by step, we have to use all this model in order to analyze our problem. So today we are going to analyze one problem, the simple problem that is a plate with a hole. Okay. So this is the geometry. So here we are using the 2D analysis. Okay. So you can see the cross section dimensions are this is 100 mm. All dimensions are in mm, and this is the 50. This length is 100 mm and this height is 50 mm. And here this left hand is fixed, and the right hand is having this pressure 10 megapascal. Okay, and there is a hole inside this plate which is of 20 diameter. So these are the material properties. Young's modulus of the steel, which is equal to the materials for this plate is steel. Therefore, E is Young's modulus is 200 gigapascal, and the Poisson's ratio of steel is 0.3. Okay, and here one is note is that ABAQUS does not have units. Okay, therefore you must use consistent units. Okay, so here these are the consistent units. When we use the length in meter, then we have to find we have to use all the corresponding quantities into these units. Means when we use the length in meter, then we have to use force in Newton, mass in kg, time in s, stress in pascal, energy in joule, and density in kg per meter cube. And when we use the SI unit in mm, then we have to use length in mm, force in Newton, and here one important thing is mass in ton, not in kg. So we have to use the mass in ton when we use the length dimension in mm. And the time in second, stress in megapascal, not in pascal. We have to use the stress in stress value or the Young's modulus value in megapascal, not in pascal, when we use the length dimension in mm. And the energy, for example, fracture energy, we give the input energy as the fracture energy in fracture problems. For that, the energy is in millijoule, not in joule only. And we have to give the input density input as a in ton per mm cube, not in kg per meter cube. Okay, so you have to remember all this consistent unit while performing the modeling and simulating activities in ABAQUS. So for this simple plate with the hole problems, we know due to this hole we get the stress concentration, and you can see here the maximum stress is around three times of the stress at this point. Okay, so that we will see after solving this problem into the ABAQUS. So open this ABAQUS window. So after clicking on this ABAQUS CAE, so you will see this window. Okay, this window. So here this window which consists of this start session. So in the create model database, we have to perform. So by using this ABAQUS, we can perform standard standard analysis or the implicit analysis. Implicit analysis is generally performed in standard ABAQUS standard, and the dynamic analysis or the uh, very high impact related analysis we can perform in the explicit domain, uh, explicit ABAQUS explicit. And third one is we can also perform the electromagnetic analysis with this ABAQUS software. So now click on this under the click model database, click on this with standard and explicit model. So here we are performing this activities in the ABAQUS standard. So now first step is to create the part. Okay, so our plate dimension is 100 by 50. Okay, and there is hole at the middle which is of 20 diameter, and fixed end is left end is fixed, and the right hand there is a pressure 10 megapascal. So let us first create the part. Okay, create part, click on this. Okay, go here. Okay, miss, click on this part manager, create. Okay, give the name here, name plate. Okay, so here we are performing 2D analysis. So click on 2D planar, deformable, means type is deformable, and the base feature is shell. Okay. Now before I forgot, sorry. Before doing any analysis in ABAQUS, we have to first uh, set the work directory. Okay. So first set the work directory. Okay. Don't save your works in the C folder. Go to the D and then create the new directory, ABAQUS. Okay. And OK. Now select this ABAQUS here and OK. Click on OK. So we have selected here the work directory in D folder is ABAQUS. Now click on this OK button. Now create the part. Okay, here go here and give the name plate. 2D planar, deformable type is deformable, and base feature is shell. Okay, and this approximate size means it is a grid size. So in the on that grid you create your part. Okay, so here we have to create the part. So use a rectangle because our plate is a rectangle. Now give the dimensions, or you can create for first whole areas. Now give the dimensions. So this dimension is 100 mm. So here I am giving all the dimension in mm. Okay, then give this, select this line and give it is at 50 mm. Okay, now give this dimension as this is a 50 mm also. And this is 25 mm. Okay. So this is the here we have sketched our part. See the all the dimensions. 50 is in a height, 100 is the length, and the hole is in the center. Okay. So click on this cross sign, cancel procedure. So you will here in the you will see the one statement here, sketch the section for the planar cell. So that is done. So click on this done. Okay, so here you can see the plate with hole. Now define the properties. Next step, the first model is completed. Now define the properties. Okay, go here or go here. Create property. So the material is steel. So give the name steel. So here only means this is a static analysis. Therefore, here we are using only the Young's modulus and Poisson's ratio. So in the mechanical model, go to the mechanical elasticity. There is a elastic. So here click here in the Young's modulus. Give the Young's modulus value in the megapascal, not in the gigapascal, but in the problem it is in gigapascal. So convert that in megapascal. 200 is a gigapascal. So 1, 2, 3. This is a megapascal and Poisson's ratio is 0.3. Okay, so this is the elastic properties we have given. We have to give only two constants, Young's modulus and the Poisson's ratio. Okay, now we have to create the section. Means why we create the section? Because that section, material sections, we are going to assign to our geometry. So here we have to create the section. Section in the section manager, go to the section manager, create the section plate section. Okay, plate, give the name as a plate section. In the go use the solid homogeneous section, select the material. Okay, steel. Okay, so here you can see the section is created, plate section. Click on this dismiss, and again we have to assign this section, steel section, to this CAD model. Now go here, create, and give the name, set name as a plate. Click the plate and click on this done button. Okay, so here we have assigned the properties, assign the section. So here we have assigned the properties by creating the section to this plate with hole. Now go to the assembly, third module as assembly. Click on this assembly, create instant. So in the there is only one part. So just click on this OK button. Okay, there is only one part. So just click on this OK button. Then the next one is the step module. So in the step module, we have to create the analysis type, or we have to define the analysis type. So create step static analysis and give a name as the static analysis. Static. So create. So here in the procedure type, select the general, and in this from this you can select the static general for this. Okay, so there are different types of analysis. When you are interested in the dynamic implicit analysis, click on this. Dynamic explicit, for example, in case of impact problem, we can use the dynamic explicit analysis. And in the when you are coupled thermomechanical problems, for that case, the temperature has one extra degrees of freedom along with the displacement. So for that case, you can use the dynamic temperature displacement, this explicit analysis. And heat transfer analysis, you can select this heat transfer, mass diffusion. There are different types of analysis. We can select the types of type analysis from this create step window. So for our case, click on this static general and continue. So here keep all the details as it is. Okay. So the time period is 1, because in the static analysis, time period is not important. So okay, keep all the details as it is. Okay. So click on OK. Then here you can use you can request the field output. So I will keep all the field output uh, uh, as it is. That is a pre-selected defaults. Okay, you can see here, because here we are only interested in the trace result. Okay, so click on this OK, and in the second here you request the history output. Okay, is what are the values of the energy with respect to time, what are the displacement, velocity, accelerations, that you can select from this button. Now steps model is completed. Now go to the interaction model. Here the interaction, there is only one part, so we can skip this interaction model. If there are two, three separate geometries, then we have to use this interaction model, and we have to define the contact algorithm. There are two types of contact algorithm in the ABAQUS: general contact or the kinematic contact algorithm. So here from this model we can select that. The next, the load model. So in this we define the boundary conditions and the low loading conditions. So now first define the load or create the load. Okay, in the load model name, I will keep this name as a load 1 only, default. And at the right hand side of this plate we have to use the pressure. Okay, so in the category mechanical category, go to this types of selected step, go to the here pressure, click on this pressure, continue, and click the right hand side line. Okay, edge at the right hand side, and click on this done. Select surfaces for the load. So we have selected this right hand side edge. So click on this done. Okay, so the magnitude of the pressure is 10 megapascal. Okay, so here the direction is in x direction, therefore we have to give it is a minus 10 megapascal. Okay, so already the pressure is given in megapascal. So use enter the magnitude as minus 10. So here you can see the pressure is applied at the right end. Okay, pressure is applied at the right end. So you can use this for the zoom in button like this. The next one is a boundary conditions. Okay, here go here in the boundary condition manager, click on create, give a name as per your wish. Steps is statics, mechanical, and here the left hand is fixed, means all the degrees of freedom are fixed, means are 0. Then we have to click on the symmetry and anti-symmetry or encaster type, continue, and select so here you can read the statement, select regions for the boundary conditions. So click on this left hand and click on this done. Now here we have to fix all the degrees of freedom. Okay, so the encaster boundary conditions we have to use encaster. So here the u1, u2, u3 along with the rotational component ur1, ur2, ur3 all are 0. Therefore here we are using encaster boundary conditions. Okay, so this is the fixed boundary conditions. Now this definition of boundary conditions is completed and loading conditions. Now go to the mesh model. Okay, so in the mesh model, click on this plate because there is only one part, and click on this assign element type. So here we have to assign the element type. Okay, assign the element type. But so by default, when we use the by default mesh, then this problem will give you the unstructured mesh. But due to this stress concentration, okay, effect, and by using the unstructured mesh, we can't get the correct results of the stress. Therefore, for this problem, we need to use the structural meshing. And in order to do the structural meshing, we need to partition this plate into 4 parts. So I will first partition this part into 4 parts, our geometry into 4 parts. So use this command, partition face or sketch. Use this command from the part module. Go to the part module and use this partition face sketch. Okay, and use this zoom in command here. Okay, click on this and draw the line. Okay, center line like this from this. Okay, draw one line here and draw one line from this this point. Okay, sketch partition geometry. So here we have divided our part means geometry into 4 parts in order to uh, use the structural mesh. So sketch the partition geometry. Done. Click on done. Okay, so you can see the part is partitioned into means the geometry is divided into 4 parts, 4 different parts. Now go in the mesh module here, and then click on this assign element type here. Assign element type. Click all the regions. Select the regions to be assigned element types, and click on this done. Okay, so by default, you can see in the element library, the plane stress element is selected. So we have to use this plane stress element. Okay, with reduced integration, geometric order is linear. So all the default values we are using related to this plane stress element. So click on this. The element type is CPS4R, a 4-node bilinear plane stress quadrilateral, reduced integrations, hourless control. Click on this OK. Okay. Now now we have to assign mesh controls. So click on this mesh controls here. Select the region to be assigned mesh controls. We have selected all the our geometry and click on this done. So now here the by default mesh control is free. So here we have to click on this structural meshing. Okay, structural meshing. Click on this OK. So green color of the geometry means it is a means we can perform the structural meshing. Okay, now go to the seed parts here. First one to give the approximate global size. So here I'm using approximate global size of 2. Okay. So now click on this mesh part for the meshing. So here it is saying that okay to the mesh part. This is a question. So I will click on this yes. So this is a meshing. So there are 1200 elements. You can see the number of elements here. So 1200 elements have been generated. It's 1200 plane trace element. Okay, with reduced integration for this plate. So now this mesh model is completed. Now we are going to solve this problem. Go to the job model here, job model, and create the job. So here in the job manager, create the job. Okay, continue. After creating in the create job, continue. So click OK. Keep as it is all the default settings. Click on this OK. Okay, now submit the job. Okay, means you can check right. You can also make input file, and through that input file also you can write the you can run your job. So the extension of this input file is .inp. Okay, this is also important, or you can edit this input file also as per your requirement. So here we don't have any extra requirement. So I'm not going to edit this input file. Here I am going to only, here I will submit the job only. So here Click on OK. So job is submitted. So wait for 1 or 2 minutes. So here you can see the statement. The job input file job 1 has been submitted for the analysis. So status is running. So we can monitor the results also here. You can check are there any errors or not. You can also check the warnings. Wait. Okay, so there is no errors, and you can see the status completed. Now go to the results from here or in the from by using this visualization model. So I will click here results. So in the visualization model, you can see the results. So click on this contour plots. Means this button will give the plots contour plots on the deform shape. So click on this. So here you can see the maximum value here. The maximum value is around 2.34. I think we have to use the very fine mesh here. So that will give the values around 3 means 2.3. This is a 23.46 megapascal maximum here. So I think when we use the fine mesh, I think we can get it is around 30 megapascal. Okay. So that's it from my side. If you have any doubts, you can ask.
So if anyone has any doubt, you can raise your hand, and then again you can ask a question.
Hello, anyone? Any doubts? Basic related to the theoretical API or related to the abacus?
So Arun, there are some questions from the application form part.
Okay.
Hello?
Okay.
Uh, Means one question is that for modeling the finite element modeling, so which should we prefer, ABAQUS or ANSYS?
Both can be used. Means both can be used. Means for example, means abacus is generally used when the material model is means if you are interested in the modeling the material for the new material means there are subroutines. Na? You met means you can use them means we can write the code by using the subroutines in the abacus effectively. So that one main difference between the abacus and ANSYS. And but a lot of material model is also available in the ANSYS. But for the user material, we can prepare the abacus because we can write the subroutines in the abacus. In ANSYS also we can do, but I think when we compare the ANSYS and abacus, abacus is good.
Okay. So another question is related to same question. So like, how can CAE tools such as ANSYS, ABAQUS, LS Dyna are different in capability features to perform advanced simulation, and why other lag behind?
Okay, means I think if you see generally, means the abacus tool is generally used in the universities and the ANSYS is in industries. And but some of the industries also use both, means abacus as well as the ANSYS, and some of the universities also use both softwares. In abacus, if you see abacus, there are two models: abacus standard and abacus explicit. So in the abacus standard, we use the abacus means implicit analysis, and in the abacus explicit, we use the abacus explicit we use the means the explicit problem in this the time total time of the uh, event is very less. Means, for example, in case of the impact problem, we can use the abacus explicit, and for the small larger time, we can use the abacus standard. And and the ANSYS, the workflow of the ANSYS is very different. There are ANSYS workbench and the APDL. So the workflow is different, but I think the main thing output the approach is same. We use in both the methods we use the same approach. Means that is a finite element analysis. And in a LHDyna we generally use that LHDyna tool is generally used for the impact problem. Okay, or crash worthiness. A small time problem, small time event, we can model in the LHDyna. That is the main difference.
Okay. So, Prakhar, you can ask a question. I think you have raised your hand.
Yes, sir. Sir, can we do a user subroutine model in the academic version?
But you can no, a user subroutine is on academic version is not available, I think. Means last year we have checked and it is not means applicable for the academic version.
Sir, then how can we do the material degradation in ABAQUS academic version?
Material means we can means commercial license we can take, or if you are studying in the university or doing the working in the industries or the
Yeah, I
studying
am
in
in the
the
studying in the university, sir. So, but we have
so I
a
think if your industry have some licenses of the software, then you can do the this user subrouting in the commercial license version. No?
not academic version.
Means in your university it is not available.
No, no.
Okay. So I
We
think
have
you can miss collaborate with any person that miss there the license is available.
Okay, Arun,
If
I
that
have one question from my side. So, like, if you want to simulate a CFD problem like finite volume method, so there is open source like OpenFOAM, and there are some other sources also like yes, some other sources are there. So, are there any open source software for simulating the finite element analysis?
there are, but I think means these are the famous one. Means generally means like OpenFOAM for the CFD problems. This is the famous, but for the structural problem, generally people use ABAQUS or the ANSYS. Means there are some softwares, but um, I don't know the exact means I'm not able to recall the names, but yeah, generally these are the most preferable softwares for the structural analysis.
Okay. So if anyone other question, then you can. And what you means for academic? So if you want to differentiate between the academic problem and the industrial problem, so which software you suggest for the academic problem and which you suggest for the industrial problem?
Like both softwares can be used. Means ABAQUS or ANSYS can be used for the academic also and for the industry purpose also. There is a there is no difference. Okay, if you are interested, means if you have ANSYS, then you can also use ANSYS, or if you have any means if you have a license of the ABAQUS, then you can also use ABAQUS for the solving the same problem. Okay, you will not get the different results. Okay, but in the ANSYS, there are a lot of material models they have implemented in the material modeling section. But in the ABAQUS, there is some limitations. So that's why we have to write our own code in the Fortran, and we have to write that Fortran code. We have to attach with the ABAQUS. Okay, in order to run the simulation. That's it. Meaning for the ABAQUS, we have to write the Fortran code. So we have to study the Fortran coding in order to do the subroutine. Hello, Prakhar Singh.
sir, is there any other way to model the material degradation to check the material degradation in academic version? Expect then
Material
material degradation.
means
Like
you are asking about the means coding or?
Yeah, no. Is there any other way to check the material? Like we know that the steel are corroded sometime,
Okay.
so they can it still can pressurize the concrete to collapse. So we can do
Okay.
in ABAQUS without academic version or not?
Nahi, main thing with the academic version, the limitation with the limitations of the I think nodes or elements. There are
Yeah,
I think 100 elements or total number of elements which is equal to 100 we can use in the in the academic version. Check that now. I don't know the
two
exact,
lakh
but
ten
two
thousand. For
three
me, 2,10,000 notes.
10,000. No, okay.
2 lakh,
So
2,10,000.
10,000 it is very difficult. Means if your problem is
No,
simple
2,10,000,
like
sir.
rod. If your problem is simple, then we can do. Okay.
Okay, sir. Thank you, sir.
Hmm.
Yes, Arun, another question is that which for a civil engineering application, which one is to, means you would suggest for the civil engineering application?
Pratyush, can you speak loudly? I am not able to
I'm asking
hear.
that for the application related to civil engineering, so which software would you recommend?
Civil engineering also means structural. Means generally civil people also do the structural analysis, so they can also use the ABAQUS and ANSYS. There are other softwares, but mostly these two softwares are famous for the structural analysis. There is an Astra and LH Dyna also for the impact problem. Okay, but ABAQUS and ANSYS means if you are interested in the finite element analysis, then start with these two. Means any one softwares. So the procedure is same. So anyone means the finite element analysis, we can use the ABAQUS or ANSYS.
So I
Anyone.
think there are some general questions. Mostly other questions is asked from the particular background, like analysis, factor analysis, and the composite analysis. So I think this will require some more other sessions. So with the help of Arun and some other mentors, we are planning one course with finite element method within the sessions. And we will share you the details in the group as soon as possible. So I hope you have enjoyed this session. And if you have any other questions, you can ask and we can chat with others related to your program anytime. Okay. So I think we can end the discussion if you have any questions. Okay. So thank you, Arun, and thank you everyone for joining this session. So have a
Okay, thank
nice,
you.
nice day.
Thank you
Thank
all.
you.
Thank you, sir.